Here's something strange about forces. Take a cart on a ramp pulled by a spring. The spring pulls on the cart. That's a real force, and it changes the cart's momentum. Now enlarge your definition of the system to include the spring. Suddenly that same force does nothing to the system's total momentum. Nothing physical changed, only the boundary moved. Start with a concrete setup. A cart rests on an inclined plane. A spring runs from the cart up to a force sensor fixed at the top of the incline. Three forces act on that cart. First, the spring force, the pull of the spring on the cart. Second, the gravitational force between the earth and the cart. Third, the contact force from the inclined plane pushing back on the cart. Three forces, three different partners. The spring, the earth, and the plane. Now draw a boundary, enclose just the cart, and call what's inside the system. Everything outside, the spring, the earth, the plane, is the surroundings. Every one of our three forces crosses that boundary. Each one comes from outside and acts on something inside. So all three are external forces. Their vector sum is what we call the external force on the system. The external force equals the spring force on the cart, plus the gravitational force on the cart, plus the contact force on the cart. That sum is the only thing the cart feels. Newton's second law says that net force equals the rate of change of momentum. Integrate both sides over time, from an initial time to a final time, and you get the impulse form. The change in the system's momentum equals the integral of the external force with respect to time. We give that integral a name, the impulse on the system. So the external force accumulated over time is exactly the momentum the system gains. This is still one object, but written in the language of systems. Now move the boundary. Draw it around the cart and the spring together, two interacting objects in one system. The spring still pulls on the cart, and the cart still pulls back on the spring. But both of those forces now live inside the boundary. They are internal forces. By Newton's third law, they are equal in magnitude and opposite in direction, and they act on two different members of the same system. Gravity and the plane's contact force are still external. Meanwhile, a new external force appears. The spring is attached to the force sensor and the sensor sits outside. Add the internal forces up. The force of the spring on the cart plus the force of the cart on the spring is the zero vector. That is the whole content of Newton's third law. Sum over the entire system, and every internal force finds its partner, so the total internal force is zero. Write the total force on the system as the external force plus the internal force. The internal piece vanishes, and the total force equals the external force alone. The spring force has not disappeared, it has simply stopped counting. Generalize. Take a system of m particles, labeled by an index that runs from 1 up to n. Pick out the ith particle. The total force on it splits into two pieces. The external force on that particle from anything outside the system, plus the sum of the forces from every other particle inside the system. That sum runs over Oj, not equal to I, because a particle cannot push on itself. Equivalently, define the force of a particle on itself to be zero. That second piece is the internal force on the ith particle. Now add up the forces on every particle in the system. The total force is the sum over I of the force on the IC particle. Split it, the sum of all the external forces, plus a double sum over every ordered pair of distinct particles. Look at that double sum. Every term in it has a twin. The force of particle J on particle I appears somewhere, and so does the force of particle I on particle J, and by the third law, those two add to the zero vector. Pair them off, and the entire double sum collapses to zero. What survives is the external force. Bring momentum back in. For each particle, Newton's second law says the force on it equals the time derivative of its momentum. Substitute that into what we just proved. The external force on the system equals the sum over all particles of the time derivative of each particle's momentum. Now define the momentum of the system as the vector sum of the individual particle momenta. Momenta act as vectors head to tail. Because differentiation is linear, the sum of the derivatives is the derivative of the sum. So the external force equals the time derivative of the system's momentum. Integrate that result over time, exactly as we did for the single card. The change in the system's momentum equals the integral of the external force with respect to time, from the initial time to the final time. Call that integral the impulse on the system. This is Newton's second law generalized. It holds for a cart and a spring for a galaxy, any collection of particles you care to draw a boundary around. Only what crosses the boundary can change the momentum inside. So the boundary is a choice, and it is the most powerful choice you make. Draw it small and the force is external, changing your system's momentum. Draw it large enough to swallow both partners of a third law pair, and that same force falls silent. Physics does not change. The bookkeeping does. Choose the boundary well, and the messy internal traffic disappears, leaving only the few forces that reach in from outside. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.